On July 21st, 2023, at a moment almost nobody on Earth actually noticed, something went badly wrong in the single most remote place any human-made object has ever traveled to. A machine sitting 12.3 billion miles away from us, a machine that had been faithfully talking to Earth every single day for 46 straight years, suddenly went quiet. Not entirely quiet. A faint carrier signal was still technically detectable, a kind of mechanical heartbeat proving something was still alive out there. But the actual data, the continuous stream of scientific readings that had been flowing home without a single major gap since 1977, simply stopped. Engineers at NASA's Jet Propulsion Laboratory in California looked at their monitors and saw nothing but silence where there had always been signal. And then they realized something that made an already bad situation considerably worse. They couldn't just fix it, not because they lacked the skill or the knowledge, but because fixing it meant sending a command across 12.3 billion miles of empty space, waiting 18 and a half hours just for that command to arrive, and then waiting another 18 and a half hours after that to find out whether it had actually worked. And the specific nature of the problem they were dealing with made it entirely possible the command would never even reach the spacecraft in the first place. This is the story of what happened to Voyager 2 during the summer of 2023. How it went silent, how a small team of engineers attempted something the mission's own project manager openly admitted had a low probability of actually working, and what the spacecraft ended up revealing once its silence finally broke. Because what Voyager 2 has continued discovering in the years since, that scare is something that the scientific models built to describe our own corner of the universe simply did not predict. And some of what it found carries implications that reach well beyond the spacecraft itself. If stories like this one are your thing, go ahead and subscribe, because we go this deep into real science every single week. Now let's rewind to the very beginning. Voyager 2 launched on August 20th, 1977, 16 days before its twin spacecraft, Voyager 1, despite carrying the lower mission number. Both probes were heading out toward the outer planets, but Voyager 2 was given the more ambitious route, a genuine grand tour that would carry it past Jupiter, Saturn, Uranus, and Neptune in sequence, using the gravitational pull of each planet as a slingshot to fling it toward the next one in line. That specific planetary alignment, the one that made the entire grand tour geometrically possible in the first place, only lines up roughly once every 175 years. The engineers working in the 1970s knew full well they had exactly one window to pull this off, and they used it. What was supposed to happen after that planetary tour wrapped up was, frankly, supposed to be uneventful. Both Voyager spacecraft were expected to gradually drift outward, slowly lose power, and eventually fade into permanent silence somewhere out in the far reaches of the solar system. The mission itself was originally designed to deliver roughly 5 years of primary scientific data, maybe a little more if things went well. But the spacecraft simply refused to cooperate with those modest expectations. They kept going. They kept transmitting. They kept functioning on technology that the modern engineers currently maintaining them sometimes describe as almost miraculously durable, considering it was designed before most of those engineers were even born. By the time 2018 rolled around, Voyager 2 had been operating continuously for 41 years, and it had become just the second human-made object in all of history to cross the heliopause, the boundary where our sun's protective influence finally ends and the true empty space between stars begins. We'll come back around to exactly what it found at that boundary shortly, because the findings there are genuinely extraordinary. But first, let's get into the silence. To really understand what happened in July of 2023, you first need to grasp one fundamental constraint that governs absolutely everything about operating a spacecraft this astonishingly far from home. Radio signals travel at the speed of light, and nothing in the universe travels faster than that. Voyager 2 is so far away right now that even a signal moving at the literal speed of light takes 18 and a half hours just to reach the spacecraft from Earth. Then it takes another 18 and a half hours for any response to travel back. That's 37 hours minimum for a single complete exchange of information. You send a question, you wait 37 hours, and only then do you get your answer. If that answer requires any kind of follow-up action, you wait another full 37 hours on top of that. Every single diagnostic step, every test, every tiny adjustment operates on this brutal timeline. There is no workaround, no shortcut, no clever engineering trick around it. The physics simply do not negotiate. On July 21st, 2023, a team working at JPL was uploading a routine series of planned commands to Voyager 2, the kind of scheduled maintenance instructions the team had been successfully executing for decades without incident. But somewhere buried inside that particular sequence of commands, an error crept in. The wrong version of a command got transmitted, and the effect of that single mistaken command turned out to be precise and genuinely devastating. Voyager 2's high-gain antenna, the large dish responsible for both receiving commands from Earth and transmitting all of its scientific data back home, tilted 2 full degrees away from the direction of Earth. 2 degrees sounds trivially small when you say it out loud. In most ordinary engineering contexts, a 2-degree error would barely be worth mentioning at all. But at a distance of 12.3 billion miles, 2 degrees of angular error becomes absolutely enormous. From Voyager 2's position out there, Earth is a vanishingly tiny target in an ocean of empty space, and the dish has to point with extraordinary, almost surgical precision, just to maintain any kind of usable data link at all. 2 degrees off was more than enough to break that link completely. Voyager 2 could no longer receive commands from home. It could no longer transmit any readable data back. And the team on Earth, for all of their combined expertise and all of their sophisticated equipment, could do almost nothing about it, because the very commands they'd need to send in order to fix the misaligned antenna could not reach a spacecraft whose antenna was no longer even pointed in their direction. The team quickly assessed what options remained available to them, and there weren't many. Option 1 was to attempt an extremely high-power transmission from one of the Deep Space Network's most powerful ground stations, and simply hope that enough of the signal would reach the spacecraft, even with its antenna sitting slightly off target. The mission's project manager, Suzanne Dodd, was refreshingly direct about the odds when she spoke to reporters. She said there was a low probability that the attempt would actually succeed. Not zero, but low. Option 2 was simply to wait. Voyager 2's onboard software is programmed to automatically reset the spacecraft's orientation several times a year as a built-in safeguard against exactly this kind of scenario. The next scheduled reset was set for October 15th. That was the guaranteed fallback solution. But October 15th was still months away, and the scientific community was understandably not thrilled about the prospect of losing that much irreplaceable data. From a spacecraft currently operating out in interstellar space, a region humanity may not have another working instrument stationed inside for decades to come. Through the final days of July, the team did something careful, methodical, and quietly nerve-wracking. Using multiple ground stations across the Deep Space Network simultaneously, they simply listened for Voyager 2. Not for actual data, just for the carrier signal. A carrier signal is the basic underlying radio frequency that any actively transmitting spacecraft continuously broadcasts. A kind of electronic heartbeat confirming the hardware itself is still running, even if nothing useful is being communicated on top of it. Finding that carrier wouldn't restore any lost data, but it would at least confirm the spacecraft was still alive and still tracking along its expected trajectory. On August 1st, 2023, they found it. Stations across the Deep Space Network picked up Voyager 2's faint carrier signal. It was noticeably weaker than normal since the antenna was tilted away from Earth, but it was undeniably there. The spacecraft was alive. That detection changed the entire calculation for the team. It confirmed something genuinely important. Voyager 2 was physically intact and operating normally in every other respect. The problem really was purely one of antenna orientation, nothing more catastrophic than that. And the carrier signal detection told the team something else, too. If they could pick up that faint carrier, then maybe, just maybe, a sufficiently powerful transmission sent from Earth could reach the spacecraft's antenna even at its current misaligned angle. On August 2nd, 2023, they made the attempt. The Deep Space Station, located near Canberra, Australia, the facility in the southern hemisphere with by far the best geometric alignment relative to Voyager 2's current position, fired off what the engineers themselves ended up calling an interstellar shout. It was a 100 kilowatt S-band radio signal transmitted at absolute maximum power, aimed squarely at the last known position of a spacecraft, whose receiving antenna was currently pointing in the wrong direction across a gulf of 12.3 billion miles. The command embedded inside that shout was simple and specific. Turn the antenna back toward Earth. The signal left Earth on August 2nd, and the team now had absolutely no choice but to wait 18.5 hours for it to travel out to Voyager 2. If the spacecraft actually received it and successfully executed the command, they'd then need another 18.5 hours for any kind of response to travel all the way back home. The total wait, if everything went perfectly, was 37 hours. It's worth briefly appreciating the infrastructure that made this rescue attempt even possible in the first place, because the Deep Space Network itself is one of the most extraordinary engineering systems humanity has ever quietly built, and almost nobody outside the space science community knows it exists. It's a coordinated global array of large radio antenna stations positioned at 3 points around the Earth, one near Goldstone in California, one near Madrid in Spain, and one near Canberra in Australia, spaced roughly 120 degrees apart in longitude, so that as the planet rotates, at least one station always maintains a clear line of sight to any spacecraft in deep space. The largest dishes at each site measure a full 70 meters across, among the most sensitive radio receivers ever built, capable of detecting whispers of electromagnetic energy that have traveled across billions of miles. The Canberra station was chosen specifically because Voyager 2 is heading in a southern direction relative to the solar system's equatorial plane, giving that Australian dish the best possible angular alignment. Radio waves don't weaken the way sound does through air. They spread outward, diminishing with the square of the distance traveled. So by the time the signal reached Voyager 2, it had become extraordinarily faint. But faint enough to still reach the antenna, even misaligned by 2 full degrees, turned out to be exactly enough. Now, try to imagine the actual experience of the engineers sitting there waiting for confirmation. The shout was sent on August 2nd at a specific, carefully logged time. 18 and a half hours later, that signal would theoretically arrive at Voyager 2. If the spacecraft received it, processed it correctly, and successfully executed the reorientation command, its antenna would physically swing back around toward Earth. It would then need additional time to confirm its new position and begin transmitting again. That new transmission would then need another 18 and a half hours to travel all the way back home. The team knew the absolute earliest possible moment they could receive any confirmation was approximately 37 hours after the original command was sent. They also knew that silence at exactly the 37-hour mark wouldn't necessarily mean outright failure, since there were genuine timing uncertainties around exactly when the spacecraft might execute the command, and precisely how long the physical reorientation itself might take. So the team sat inside a window of real, gnawing uncertainty, knowing only that somewhere between 37 hours and some larger, less certain number of hours, they would either start receiving data again, or they would get absolutely nothing. At 12:29 in the morning, Eastern Time, on August 4th, 2023, roughly 37 hours after the shout had been sent, Voyager 2 began transmitting science and telemetry data once again. The antenna was pointing at Earth. The command had worked. The spacecraft was operating completely normally and remained precisely on its expected trajectory. 14 full days of silence ended not gradually, but suddenly, the exact moment the newly reoriented antenna locked back onto home and immediately began sending down everything it had collected during the gap. The reaction from the people actually present in the control room that night has been described afterward as genuine, unguarded relief, the specific kind that only comes after spending days sitting with the very real possibility of a permanent, irreversible failure, and then watching that failure simply not happen. Suzanne Dodd later told reporters they were happy and added that engineers working on these old, aging spacecraft develop a genuinely real emotional connection with them over the years, and that having Voyager back online again felt like having a member of the team finally come home. The entire silent period, from the initial command error all the way through to full communication restoration, lasted 14 days. 14 days during which the only human-made object currently sitting in interstellar space was flying silently through the void between stars, with absolutely nobody back on Earth able to hear a single word from it. And here's what makes that 14-day window significant, far beyond the immediate drama of the rescue itself. Those 2 weeks marked the longest single communication gap in Voyager 2's entire 46-year mission history. 46 years of nearly unbroken contact, and one small 2-degree antenna error very nearly ended it for good. The backup plan, that automatic October 15th reset, would almost certainly have eventually worked on its own. But almost is a word that carries a tremendous amount of weight. When you're talking about a spacecraft, you fundamentally cannot repair, and absolutely cannot replace. It's also worth putting Voyager 2's antenna scare side by side with a separate, more extended communication crisis that struck its twin spacecraft a few months later. In late 2023 and into 2024, Voyager 1 suffered the failure of a memory chip inside its flight data system, causing it to transmit nothing but corrupted, unreadable data for roughly 5 straight months. That crisis was categorically different in nature, even if it shared the same underlying stakes. The antenna issue was a physical orientation problem, correctable with a single, well-aimed command. The memory chip failure was internal hardware deterioration that required engineers to essentially redesign how the onboard software was stored and executed remotely across a 22-hour one-way delay, using programming languages already considered obsolete since the 1970s. Both crises shared the same underlying pressure. Every wrong step could be the final step, with no repair crew and no way to physically inspect anything from 12 billion miles away. Both ended in successful recovery, and both left the scientific community keenly aware that the window for data from these 2 aging spacecraft is finite, shrinking, and ultimately irreplaceable. There's a dimension to this entire story that pushes it beyond ordinary engineering and into something considerably harder to neatly categorize. Voyager 2 was designed, built, and launched by people who are now in their 70s, 80s, and 90s. Some of them have already passed away. The spacecraft they built has now outlived its original planned mission by roughly 4 decades, and it's currently being maintained by a newer generation of engineers who weren't even alive when it first launched back in 1977. The institutional memory of exactly how it works, what its particular quirks are, which commands are safe to send, and which commands must never be sent under any circumstances, is held by a small dedicated team at JPL that spends its working life in ongoing communication with two machines that most of the rest of the world has long since forgotten even exist. When something goes wrong out there, there's no manual written for that exact situation, because nobody has ever encountered it before. There's only careful reasoning, genuinely creative engineering, and the sober acceptance that the margin for error is essentially zero. What those engineers ultimately recovered back in August of 2023 is still operating today, right now, as you're watching this. Voyager 2 is further from Earth at this moment than it has ever been in its entire history. Its power supply is weaker than it has ever been. Its instruments are fewer in number than at any earlier point in the mission's 46-year run, since components have been progressively and permanently shut down over the years to conserve the spacecraft's steadily dwindling electricity supply. Its power source continues to decline at a rate of roughly 4 watts per year, and instruments are being selectively powered off, one by one, to stretch the mission's remaining lifespan as long as humanly possible. Earlier this year, following the exact same pattern already established with Voyager 1, another onboard instrument was permanently powered down specifically to preserve enough electricity to keep the remaining science instruments functioning a little while longer. Every single one of these shutdowns is a permanent closure. There's no switching anything back on once the power required to run it simply no longer exists. But the ones that remain are still measuring things right now, still recording the properties of an environment that no other instrument humanity has ever built has direct access to, still faithfully transmitting home in the thin, faint signal of a spacecraft running entirely on the residual heat of slowly decaying plutonium. When it eventually does go silent for good, sometime in the early 2030s, according to current projections, the loss won't be widely reported in most places. It almost certainly won't make the front page of any major newspaper. But inside the specific scientific community that studies the boundary of our solar system and the interstellar medium that lies beyond it, the end of Voyager 2's transmissions will quietly close a window that took 46 years to open in the first place, and one that cannot realistically be reopened on any near-term timeline, since no replacement mission has currently been funded or designed, and no spacecraft is presently on a trajectory toward that same region of space within any time frame that matters for the researchers actively working with the existing data today. Now let's turn to what Voyager 2 actually found at the precise moment it crossed out of our solar system entirely, back on November 5th, 2018, because this is where the story stops being purely about engineering heroics and becomes something considerably stranger. That specific date was identified with real precision by carefully examining sudden changes in the spacecraft's instrument readings as it crossed the heliopause and entered true interstellar space for the very first time. The heliopause is the outer boundary of the heliosphere, the enormous protective bubble of solar wind that our sun continuously generates, a bubble that encloses our entire solar system inside it. Everything within that bubble, every planet, every moon, every asteroid, every comet, and every single human being who has ever lived, exists entirely inside this protective envelope. Everything outside it is a fundamentally different environment altogether, the cold, dense, ancient plasma that fills the space between the stars. Voyager 1 had actually crossed this same boundary before Voyager 2, back in August of 2012. But when Voyager 1 made its crossing, it had a significant problem. Its dedicated plasma science instrument, the specific device designed to directly measure the properties of plasma on both sides of the heliopause, had already stopped functioning back in 1980, decades earlier. Scientists were still able to study that first crossing using its other remaining instruments, and they learned a great deal from it. But the most direct, most precise way of actually measuring what was happening to the plasma itself simply wasn't available to them at the time. When Voyager 2 made its own crossing in 2018, its plasma science instrument was still working. That was genuinely not a guaranteed outcome. The instrument was 41 years old at that point, running on a spacecraft powered entirely by decaying plutonium, surviving in conditions it was never originally designed to endure over anything close to this kind of long-term time frame. But it was working. And precisely because it was working, Voyager 2 was able to hand scientists something they had genuinely never possessed before: the first direct real-time measurement of plasma properties on both sides of the heliopause, captured by an instrument physically passing straight through the boundary itself as it happened. What those measurements ultimately revealed produced 5 separate research papers, all published simultaneously in the journal Nature Astronomy in November of 2019, roughly 1 year after the actual crossing occurred. And critically, the findings across all 5 papers were not what the existing models had predicted at all. The heliopause itself turned out to be dramatically thinner and considerably sharper than any model had previously suggested. Researchers had generally expected a gradual transition zone a broad region where solar wind plasma and interstellar plasma would mix together and blend gradually over some meaningful distance. What Voyager 2's plasma instrument actually recorded instead was a transition that occurred in less than a single day of travel time. The boundary separating the two completely different environments wasn't a gradual fade at all. It was almost a hard line. Solar wind plasma sat on one side, interstellar plasma sat on the other, and the transition between the two was sharp enough that the instrument was able to capture it essentially as a single discrete event, rather than as any kind of extended gradual crossing. The interstellar plasma sitting on the far side of that boundary also turned out to be considerably hotter than anyone had expected, and this particular finding generated an enormous amount of discussion inside the research community afterward. The existing models had confidently predicted that interstellar plasma near the heliopause should be cold. What Voyager 2 actually measured was a temperature significantly higher than any of those predictions had suggested. And unlike Voyager 1, which had been unable to directly measure plasma temperature at its own earlier crossing, Voyager 2's still-functioning plasma instrument gave scientists genuine hard numbers to work with, rather than the indirect inferences researchers had been forced to rely on previously. Those numbers simply didn't match what the model said should be sitting out there. The magnetic field findings added yet another layer of genuine complexity on top of everything else. Voyager 2 encountered something researchers ended up describing as a magnetic barrier, sitting in the region just inside the heliopause, a specific zone where magnetic field intensity increased sharply and unexpectedly. According to the paper, analyzing the spacecraft's magnetometer data, this barrier strongly influences exactly how cosmic rays are able to enter the heliosphere from outside its boundary. Cosmic rays are extremely high-energy particles produced by distant supernovae and other violently powerful events happening across the wider galaxy. The heliosphere partially shields our inner solar system from a considerable amount of this radiation, but the specific mechanism behind that shielding, the precise way the magnetic field at the boundary actually interacts with incoming cosmic ray particles, turned out to be far more structured and considerably more complex than any of the pre-crossing models had actually described. If you want to keep following this story as it continues to develop, subscribe right now, turn on notifications, and drop a comment below telling us exactly what surprised you most in this video. Because what Voyager 2 found the precise moment it crossed the edge of our solar system is something 5 completely separate teams of scientists felt was significant enough to publish 5 completely separate research papers about, all on the exact same day. And none of those papers ended up telling quite the story the textbooks had been expecting all along.